Okay, well, that was interesting. The Zoom was not working. I had to reboot my computer just to get it going again. So that's what just happened. I don't know if you had issues on your side, but when I tried to turn it on, it just refused to work. So anyway, but we're here now. That's all that matters. So let me get some of the stuff open that we're going to need. So, oh yeah, here we are. Um, we're up to chapter 8 now. And so we're not done. Obviously, we're not done with 8. We just started it yesterday, but um, we'll just carry on with 8. And then if there's time, we'll at least take a peek at chapter 9, which I actually just posted on Moodle, as it turns out. In fact, let's get Moodle open here. And let's see what goodies we have waiting for us today. All right. Just look at my list, who's here today. Okay. All right. So what I did was, because I don't want you to have no new material. So just as a precaution, I posted chapter 9 here, along with the problem set. And also there's a new table here, which we'll investigate, if not today, certainly tomorrow, the so-called T table, which we'll see what that's all about in chapter 9. And then everything else here is what we saw yesterday. I posted the rest of the notes for chapter 7. And anyway, so everything is up to date here. And so let's get back to 8. So hold on a second. Okay, so yes, let's get that out of there. All right, so where did we leave off? Well, all right, let's take a step back and remind ourselves what exactly we're doing in this chapter. Well, first of all, we're looking at a very different type of probability distribution from what we're used to seeing. Normally, probability distributions are based on either some kind of an experiment or possibly a population or a sample. Here, we're focusing our attention on samples. In other words, what we're seeing here is that when we draw samples from a population, every time we draw a new sample, obviously the numbers that we get will be very different, or at least different. They don't have to be very different, but they will be somewhat different. And so every time we draw a sample, if we calculate a sample mean, that means that each sample will have a somewhat different sample mean, as we saw in some of our examples. In fact, we have a chart here it is, where we showed an example where we took a sample of 5 people and asked their ages, and we repeated this process 10 times. So these boxes represent the actual ages of the people that we questioned. And in the first sample, you can see the average age turned out to be 35.2 based on these 5 ages. The second sample, that turned out to be 55, and then you can see that in the third sample was 52.6. So the key detail here is that from one sample to the next, the means are going to be different from each other. And in fact, in this example, they can be quite a bit different. In fact, you can see that one sample had a mean of 19.2, and this one had a mean of 74. Now, logically, it stands to reason, though, that when you have such small samples, there's a very high probability that the sample means can be very different from one group to the next. So when we only have a small sample like this, there can be a tremendous amount of variation from the sample means that we obtain from each of these samples. And in fact, I drew a little histogram to illustrate these results. And you can see that the sample means are pretty much scattered all over the place. There's no real pattern to them here. And what happened, though, was that then I changed the sample size to 20, although I didn't show the actual results. If you imagine now that I go out into the mall, and instead of taking 5 people at a time, I take 20 people at a time, and in each group, I calculate the mean or average age, then the results will be very different. The more people that there are in each group, the higher the chances are that the means will be very similar to each other. Okay, in fact, that's exactly what happened. And you can see the histogram here shows that when I had a sample of 20, the mean age was actually always between 30 and 70. And most of them were clustered in the center like this, unlike the previous case where they basically were scattered around from as high as 80 to 90 to as low as 10 to 20. So what's going to happen is that if I keep increasing the sample size, eventually these bars will come to resemble more closely the normal distribution. And we know that because of a key result in statistics called the central limit theorem. Okay, so according to the central limit theorem, if we draw our samples from a normal population, then the distribution of these X bars will be normal. Okay, so remember, these bars represent sample means, or X bars, and so their distribution will be normal if the underlying population is also normal. And even if it's not normal, the sample means will be normally distributed as long as we choose samples of at least size 30. Okay, once we hit 30, it no longer matters what the underlying population is. These sample means will have a normal distribution. Although it may not be perfectly normal, it could be a little bit off, but it's close enough that we can justify using the normal distribution to calculate our probabilities in this chapter. Okay, so now the cases where you have a non-normal population and a small sample, we will not deal with those here. Okay, that has to come later. So in this chapter, you can assume that for all the problems that we will encounter, you can go ahead and use the normal distribution. All right, but just be aware that these requirements are going on behind the scenes. So in a different chapter, you might find yourself needing to use a different probability distribution than the normal distribution. All right, so what else did we cover in this chapter? Well, we started to talk about the moments. Now, a sampling distribution, or the sampling distribution for X bar, we've already seen is considered to be normal, but we also have to specify the moments of this sampling distribution. Now, of course, the moments themselves are the same as they are for the other distributions that we've seen. We have an expected value, we have a variance, and we have a standard deviation, although when we're dealing with sampling distributions, we have a different name for the standard deviation. We now are going to call it the standard error. Okay, so don't be confused. They both mean the same thing, but the words standard error are used specifically for this situation when we're dealing with a sampling distribution. So, but if you call it a standard deviation, you're not technically wrong. It's just that it's more convenient to have separate names for the population standard deviation and the standard deviation or error of the sampling distribution. So there are formulas for each one, of course, and there's also new notation. Okay, in order to distinguish these moments from what we've seen with our other cases, we're going to introduce some slightly new notation. Okay, and you'll notice what that consists of is using a subscript of X bar for each of these cases. So in other words, when we're dealing with a sampling distribution, the mean or expected value is going to be written as, actually there's two things we could call it. This is written as either mu X bar, or else sometimes you see it written as the expected value of X bar. They both mean the same thing. Okay, now the variance, we're still using sigma squared, but now we've got this little subscript to remind us that this refers specifically to the sampling distribution of X bar, so that there's no doubt in your mind about what we're being asked to do. And then the standard deviation or standard error is sigma with a subscript of X bar. Now, that raises the question, how do we calculate these measures or moments? Well, there are formulas, of course. And so the expected value is easy because all you have to do in a case like that is use the population mean. Okay, so remember, we're drawing samples from a population of some kind, and the population has a mean of some kind. So the population mean, as you recall, is represented by the Greek letter mu. And of course, the population standard deviation is represented by sigma. Okay, so for the sampling distribution, of X bar, the expected value, or mean, is equal to the population mean. It's that simple. And you can kind of see why, because I mean, if you're drawing samples from a population where the mean value is, let's say, 100, if you pick enough samples, the average of all those sample means that you've calculated will have to be very close to 100. So we're assuming that the mean of these X bars equals the actual population mean. All right, now the tricky ones are the variance and the standard error. So for those, we have to introduce a new concept, I guess. What we have to do here is make a distinction between what we're going to call large samples and small samples. Okay, so if you recall, lowercase n is used to represent a sample size. Capital N is the population size. So we're going to define large. A large sample indicates that the size of the sample is less than or equal to, more than 5% of the entire population. We can also express this as n over n. In other words, what this is saying in English is that the sample size is more than 5% of the population size. That's, in this context, this is what we will define as large and small. So of course that implies that small just means the opposite, less than or equal to 5% of the population. And the logic behind this comes from the central limit theorem. So we're not going to get into the details, but this is the cutoff point. This was determined through historical experience. You know, the thing about statistics is a lot of these results were derived from real world data. This is a very different situation than you might find in, let's say, in calculus, where the results are demonstrated through proofs. In statistics, the results that we see are typically based on actual experience. So here, for example, we'll just define a small sample as, of course, that would indicate that the sample size is no more than 5% of the population, or we could write it like this. Okay, so we hear the sample size is 5% or less of the population size. All right, so just a couple of quick examples. I'll just quickly make up some new numbers. For example, if the population consists of, let's say, 1,000 people's ages, then a sample of 100 would be considered large. And let's say a sample of, because that's 10%, whereas a sample of, let's say, 45 would be considered to be small, since this is 4.5% of the population. So that's how we tell them apart, large and small. Okay, now with all that being said, then we can formally define the correct calculations for our variance and standard deviation or standard error. Okay, so we'll make a chart here. Okay, so the variance here will be sigma squared over n, and with a large sample, we have an extra term here. Now, I'd like to point out that this term, if you look at it, if n is at least 2, the lowercase n rather is at least 2, then this expression in parentheses is going to be a number which is less than 1. So in other words, when we have a large sample, what we're basically saying is that the variation from one sample mean to the next should be smaller than with a small sample. And so we're going to try to adjust for that fact with this extra term here. Now, the standard error, of course, is simply the square root of what you're seeing above. Okay, so that's all you need to know about these two measures or moments. Now, this piece in statistics has a special name. Let me just mention that here. This is often called the finite population correction factor. This one up here doesn't seem to have a name. I don't know why, it just doesn't. But here, the square root is called the finite population correction factor. And again, the point of it is to reduce the standard error to account or to take into account the fact that the sample is relatively large, which means that the sample means should be much closer to each other than for a small sample. All right, now with all that being said, what we can do now is calculate probabilities based on the normal distribution and on these moments. All right, so I think it's time to look at an example. All right, let me just give you a minute to finish copying that. All right, and then we'll carry on. Oh, let's see who's here today. Everybody's here. Okay, good. All right. Boy, everybody's camera shy in this class, aren't they? Yes, they are. All right, let's get that out of the way. So let's take a look. Yep, and there's our friend, the finite population correction factor. Okay, oh, one more thing. If you do want to use a table, a standard normal table to calculate these probabilities, this is the formula that you'll use. Okay, now you can see the similarity with this and what we were doing in the previous chapters. It's the same exact logic, except that now we're specifically dealing with samples rather than the entire population. So you notice the difference in the notation, but this is actually the same exact reasoning. This is how we convert X bar. Now remember, X bar is considered to be normal. So that's why we can create the so-called Z-score. and take whatever X happens to be and convert it into a z-score before we calculate any probabilities using the table. Okay. All right. And of course, once again, we'll remind ourselves that Z represents the standard normal distribution. The table is based on this. Also, you may not have noticed this in your calculators, but if you do not tell your calculator, when you calculate normal probabilities, remember with normal CDF, you're being asked for the lower limit, the upper, the mean, and the standard deviation. If you don't tell the calculator, it will assume that these are 0 and 1. Okay, in other words, the calculator, the TI 83, 84, whatever you happen to have, assumes that mu equals 0 and sigma equals 1. If you don't tell it something different, it will assume that that's what you mean. Okay, so by default, the calculator is assuming that you're dealing with the standard normal distribution. You might not have noticed that, but that's what it's doing. And in fact, in many cases with the calculator, it is making certain assumptions that you can change, but if you don't, it will assume certain values for these variables. All right, and of course, actually, you know what, let me do one more thing here. Let me draw a little diagram. So in other words, we're taking our X bar distribution, it's normal. And then let's say over here we have mu X bar plus the standard error. And over here, well then this is X bar's distribution. Down here, we have the Z or standard normal. And so this corresponds to 0. This corresponds to 1. And this corresponds to -1. Okay, this is exactly what we've seen before. And if you want to carry it out a little further, let's say we have mu X bar minus 2 sigma. Over here we have mu X bar plus 2 sigma. This corresponds to a 2, and this is -2. And that's the nice thing about the Z, these so-called Z-scores down here on the bottom are interpreted as how far away from the mean are we? How many standard deviations are we away from the mean? Okay. All right. So finally, at long last, we get to do an actual example. We have a population of 10,000 stocks. We own 10,000 stocks in our portfolio. Well, actually, this is a hedge fund. It's not an individual. The hedge fund owns 10,000 stocks. In that population of stocks, we know that the mean is 10% and the standard deviation is 20%, which when we do our calculations, we'll actually convert this to decimals. Okay, it's just easier, I think. And then what we're going to do is we're going to randomly select a sample of 100 of these stocks. So far we know. All right, so we know 3 things. And the sigma is 0.20. And the sample size is 100. Okay, so we're looking for 3 probabilities. I'm going to rewrite this as 0.08, 0.12, and between 7 and 13. Okay, now, how do we do this? Well, because X bar is normally distributed, the only thing we really have to do before we use the normal either the tables or the normal CDF function on our calculators is we have to determine the values of, we need to find out the mean of this distribution and the standard error. These two we have to calculate before we go any further, because this is how we'll look up the values in the table or else get them out of our calculators. Now, in order to do those two numbers, the first thing we want to do is make sure we know whether or not this is a large or small sample. So the ratio of the sample size to the population size is 1%. And that means that we have a small sample. Okay, remember the threshold is 5%. We're not even close to that. This is a small sample, which means that when it comes time to calculate the so-called standard error, then we'll have the simpler formula. All we have to do is take the population standard deviation and divide by the square root of the sample size. So now it's just a question of plugging in the numbers and coming up with the actual values. All right, so small sample. So therefore, we do not need the finite population correction factor. All right, now once that's been taken care of, we can just plug away. So the mean is just 10% because that's what the population mean is. Within our sample of stocks, the mean should be 10% because the population mean is 10%. The standard error comes from the population standard deviation. This is the standard deviation of the population. And this is the sample size. Okay, so then 0.20, now remember the sample size is 100, so the standard error is 2.2 or 2%. All right, well now we know that X bar is normal with a mean of 10% and a standard error of 2%. And we can therefore now calculate these three probabilities just like we did in chapter 7. If you want to use the tables, which let me go open up those tables real fast. Then you need to make a conversion, of course. Let's see. Here we go. Normal 1 and normal 2. We have a positive table and we have a negative table. So what we're going to do in each case is, of course, subtract the mean of 10% and divide by the standard error of 2%. So when it comes time to calculate the probability that the mean is above 8%, what we're actually doing is the equivalent of asking what's the probability that z is greater than or equal to -1 after subtracting the mean and dividing by the standard error. Okay, so in other words, in this distribution, remember the mean is 10. We're looking for this probability. And on the normal, standard normal curve, this is the equivalent of this probability. Because 8% is one standard error lower than the mean. Okay, so in the table, so you're looking for -1. Now, remember, this is a negative value. We don't have a negative value in our tables. So let's go find -1 in the negative table. Let's see. There we go. This is at the intersection of negative 1.0 and 0.00 right here. And when we combine these, we get 0.1587. Okay, so in other words, this area in here is 1587. But that's not what we want, is it? So what's left must be 8413. Now, with a calculator, I've written it this way because this is how it's expressed in the TI-83. On the 84, what this represents is the lower limit, the upper, the mean, and standard deviation. This is for the standard normal curve, though. In other words, this is actually only going to be valid if you're using the standard normal distribution. You could have just as easily left the numbers exactly as they were. So remember, we're looking for the probability 0.08, which means that your lower limit is 8, your upper limit is infinity. This is the mean of the X bar. This is the standard error. So you've got a couple of options here. So in other words, here, once you have the Z-score, you can use the table. You can plug those numbers into your calculator with normal CDF, or you can just take the original data and use that with normal CDF. Either way, you'll get a probability of 8413 or 84.13%. All right. So what was the second question? We were looking for the probability now that X bar is less than 12%. All right, so here we go. So we're going to do this in two different ways. We're going to construct or calculate our Z-score by subtracting the mean and dividing by the standard error. So in other words, what this is saying that's for X bar. And for Z, we have 1 standard deviation above the mean. So they both, of course, represent the same thing. Now, this one we can look at right up in the table. Not a problem. The table is designed to look for what we call cumulative probabilities. So remember on the table, though, you have to express this as 1.00. So you can look up the intersection of 1.0 plus 0.00, which is easy because that's the first column. Let's go get it, okay? In fact, there it is right there. (84.13%). Okay, so this whole shaded area from the table is 0.8413, which means the same thing over here. Now, once you have that Z-score, you can plug it into normal CDF. This is the lower limit. The upper limit, the mean, standard deviation. Or you can take the original information and plug it right in, okay? So this is the lower limit. This is the upper limit. This is the mean of X bar. And there you go. Now, when we're done, let's notice one key detail here. The previous question was the probability that X bar was greater than or equal to 8%. And you know what? It turned out to be exactly the same. Why did that happen? Well, it's not a coincidence. Okay. What happened is the following. If the mean is 10, here's 8, here's 12. So what's happening is that this is one standard deviation above the mean, and this is one below. So let's see what I can do here. All right, so in other words, what I just want to make it clear, even with all these very awkward diagrams, is that the area above 0.08, which I'll express as, let's say, red, is exactly the same as the area below 12. And that's because of the symmetry of the normal distribution. Okay, so that's one of the, and again, that's one of the very helpful properties of the normal distribution. Later on, we'll see where this may not be the case, or at least if you go on to a more advanced class, you will find that there are many probability distributions that don't have this nice feature, and that does make things a lot more complicated. All right, well, with all that being said, the third and final case was the probability that the sample mean is between 7 and 13%. All right, so we apply our conversion formula. All right, so remember in this case, mu x bar was 10. Okay, so these numbers turn out to be plus and minus 1.5. So under the standard normal curve, we are within 1.5 standard deviations of the mean. And that turns out to be about 86.64% of the curve. So you can go look at the table. Now, if you do this with a table, it's a little bit trickier. Let me just expand on that a little bit here. So you might recall that the only way to do this is to subtract one from the other. And these can each be easily looked up in the table. So 1.5 from the positive table would be right here, 9332. And then negative 1.5 from the negative table would be right about here, yes, 0.0668. Okay, so that difference is 8664, and that's our answer. Okay. Same thing as what we found with the calculator using the z-scores. But once again, if you plug these in, if you just leave the data in its original form, this is, of course, our lower limit. This is our upper limit. This is mu x bar. This is sigma x bar. And that's our final answer. All right, so you've got multiple options here for calculating these probabilities. But the only real difference here between this discussion and chapter 7 is that you have to figure out for yourself these two values. That's essentially the main difference between the two cases. All right, now I've got one more example here. I want you to see how things are different though when we have a large sample. It's not much of a difference, but it is different enough that we would like to have a separate practice problem with these large samples. All right, so let's take a look at another example. And in this case, I'm going to tell you right up front that this time we have a large sample. Okay, so let's see why. Now, here's a portfolio, not of stocks, but of paintings. Okay, so this guy's got some real money. He's got 120 paintings worth an average, oh my God, of $1 million. Maybe this is Bill Gates' private collection. This is his house in Seattle, the one that supposedly has moving walls and all the rest of that stuff. 120 paintings, the average price is $1 million, and the standard deviation is 120,000. So this is a population now. And the mean of that population is $1 million. And the standard deviation is $120,000. So we're going to pick a random sample of 10 paintings from that collection. Now, n over n in this case is 10 out of 120, which looks like it's going to be quite a bit higher than 5%. In fact, this is 8.3%. Which is clearly greater than 5%. And therefore, this is now considered to be a large sample. What do we do now? All right, not a problem. If you recall, let's go back and revisit my little chart here. That means that we must now incorporate this finite population correction factor. This is the case on the right. In other words, just now, the last example we were looking at was based on this column on the left. Now we're dealing with this case. And it's just a little bit more cumbersome. But the basic strategy behind calculating these probabilities is pretty much exactly the same, except for this little detail. So why don't we do those calculations? That always has to come first. So yes, so this is more than 5%. And so now mu x bar is always just equal to the population mean. Now here, I plugged in all the numbers. The population standard deviation was 120,000. The sample size was 10. The population size is 120. The sample size is 10 again. So while this is a fairly messy calculation, when you're done, you'll see that your standard error is here. Now, in this case, we'll round it to dollars and cents because it is dollars. And by the way, this is where the approximation errors will start to pop up. If you do this example with the tables, you're likely to get a slightly different answer than you get from the calculators. This is part of the reason right here, because we have to round this. All right. So once those are established, then the probabilities will be straightforward to calculate. And as we've seen already, there's at least 3 different ways of doing this. So if we're going to use the tables, our formula for calculating the z-scores, the usual formula that we know very well by now, is this. And so we're subtracting for each x bar the mean of 1 million and divided by the standard error of 36,484.14. All right, now remember in the first case, we're asked to calculate the probability that the mean is above $1 million. Well, guess what? That is equivalent to a z-score of 0. Why is that? Because $1 million is the exact center of this distribution. So that would be the equivalent of asking, what's the probability that z is above 0? Now, you recall from the properties of the normal distribution that the area above the mean and the area below the mean are both equal to a half. So in principle, you don't have to even do any more calculations because you already know that this probability is 0.5. But let's just do it anyway. Now, this introduces an interesting result, though. If you take the z-score and plug it into your calculator, you'll discover that it does not give us back 0.5. It's 0.4999999. Why is that? Because the calculator doesn't have infinity built into it. We're representing that as 1.0 times 10 to the 99th, which is an enormous number, but it's not infinity. So the calculator is going to give you a number which is ever so slightly different from the true value, which is a half. So don't worry about it. You can just round it to 0.5. But this is what's going on behind the scenes. There's no actual infinity in the calculator. This is a huge number, but it still misses something at the extreme tail. And so therefore we can simply round it to 0.5. And as usual, we can then just leave the original numbers intact and put them in directly into normal CDF. Okay, so in other words, here's the lower limit. Here's the upper. Here's mu x bar. And here's sigma x bar. And you'll get the same thing. Okay, so don't be shocked when you see that 0.499999. That's what's happening. All right, the second question was less than or equal to $950,000. Now this one is equivalent, let's see, let's draw a little picture here. On the X bar distribution, this is the equivalent of being below, wow, 1.37 standard deviations below the mean. That's pretty far away. So this is going to be a very small probability. And so again, you can plug this from negative 137 in here, or we can go to our chart. Let's do that real fast and see what this looks like. So this is our lower limit. This is our upper. This is the mean. By the way, I almost forgot. Let's go back to our chart for a second for this one. 0, where is 0 on our chart? 0 is in the extreme upper left-hand corner of this positive chart. Okay, and you can see that it is in fact 0. Here's 0, here's 0, and this is 0.5, because again, the center of this distribution is 0, and half the area is below that. So if you'd chosen to use the table for that last example, you would have still gotten 0.5. All right. Now, oh, but of course they were asking for above a half, so that's not a problem because it's also a half. Okay, in other words, remember the probability was actually greater than $1 million. So therefore, you know, the area to the right though and the left are both a half. Now, for this problem, we've come up with a z-score of negative 1.37. All right, let's go find it. We have to go to the negative chart for that. Let's get these out of here. All right, negative 1.3 is here. Negative 0.07 is up here. And their intersection occurs right about here. 0.0853. And that's exactly what we have here. Very good. So it's only 8%. Now, again, if you throw the original numbers into this normal CDF function, you'll get the same thing. Very good. All right. Now there's one more, which is the interval between $975,000 and $1,025,000. With a mean of 1 million. Now here, it looks, I guess it spilled over into the next. It's negative and positive 0.69. All right, this is what we're aiming for. All right, so as usual, there's multiple ways of doing this. We can use the z-scores with the normal CDF function, and we'll get approximately 51%, 0.5098. If you're going to use the calculator, of course, I mean, the table, remember that it will be rewritten as the difference between these two. And we can easily look these both up in the table. All right, positive 0.69. And by the way, here, this is where you might run into a rounding issue. There's a fair chance that we will get not the exact same solution here, but that's okay. It'll be very close. 0.69. 75.49. And then negative 0.69 is right here. Here we go. 0.2451. All right, so let's see what that turns out to be. 0.7549 minus 0.2451, 5098. Well, it is exactly the same. That's good to know. All right, and of course, there's one more thing we could have done. Again, that means plugging the numbers that we started out with directly into this normal CDF function. Here's the mean, a lower rather. This is the upper. And this time we do have a slight discrepancy. It's only 0.003, but remember over here it was 0.5098. So that's because this 0.69 is not exactly correct. If you plug these numbers into your calculator, you'll like for the first one, for example, it's 0.685. The actual value here wait a minute, 685,229,5,253. Or that's close enough. All right, but you get the idea. In other words, it's off a bit. So what that means then, and of course the chart only goes out to two places. So you have to round it to negative 0.69 and positive 0.69. So what that means is that this number you're seeing here is slightly off. This number is actually correct. Okay, this one is a slight, it's an approximation, so it's a little bit off. But that's the reason for it right here, because if you look at the table, you'll see it only goes out to two places. So by rounding 685 to 69, we're going to introduce some rounding errors, but that's okay. It's close enough. It's not a problem. I just think you should be aware of it. Well, that was an interesting chapter. So again, you can see it is simply an extension of what we covered in chapter 7. In other words, we're saying that sampling distributions, at least for X bar, are going to follow the normal distribution with a couple of small changes. Now, if we wanted to do a sampling distribution for, let's say S, the sample standard deviation, we can do that, but it requires us to use a probability distribution that we haven't seen before. Oh, yes, the 36. All right, let me go back to that. That was the result of using the finite population correction factor, and that is shown right here. It is. All right, so in other words, the standard error of X bar here is, this is the formula that we use for a large sample. Okay, so you can see you need the standard deviation of the population. You need to divide by the square root of the sample size. And then this piece, the so-called finite population correction factor, is needed when we have a large sample. Which we did. If you recall, we discovered that the sample size here is about 8.3% of the population size. So that means it's a large sample, and we must include this population, finite population correction factor. Now you can see it's only approximately correct. It has to be rounded to dollars and cents. Once you've got that done, though, the rest of it just falls right into place. From this point on, all you're doing is literally what we did in chapter 7, which is calculating normal probabilities. So you can see this area could be very important in certain areas. Like, for example, imagine a scenario where the Food and Drug Administration is not sure if McDonald's quarter pounders really weigh a quarter pound. So what they'll do is they'll take a sample and they'll weigh them, and they'll use these techniques to determine the probability that they actually are correctly weighted given the information that they have in their samples. So sampling is a very important area, and it's used often to determine if claims made by advertisers, for example, are actually correct without actually testing every single unit that they're actually producing. Okay, so in other words, a lot of these techniques that we're learning are actually meant to help us draw conclusions about a population without needing an enormous amount of information. Okay, so we'll actually see more about that in the next chapter. Now, it's already 11 o'clock, believe it or not. You know, see how time flies when you're doing statistics. That means it's extremely interesting. Time doesn't fly unless you're doing something that's either fun or interesting or both. So if time is flying for you, that's a good sign. Okay. Now, I'm sure you've been in classes where the time was not flying. And you know why? Because they were boring or pointless. Well, that's the opposite of what we're doing here. So, that being the case, um, then we will now have time to at least start looking at the next chapter. So, that would be chapter 9. What's important about 9 is not only is it a new technique that we're going to learn, but we're going to be introduced to a new probability distribution. And that one actually has a very interesting history of its own, but it's a little bit more challenging to use it though. So we're going to use tables, but also our calculators do have this information built into them, which we'll discuss as we go along. All right. So right now, unless there's any more questions, why don't we stop for a few minutes as we always do at this time and recuperate a little. And then when we get back, we'll start the next chapter. And in the meantime, I just want to remind everyone that we've already decided, based on the calendar, let's take a peek. We're going to have 3 things due next week on the 11th, the chapters 6 and 7 problem sets and the first midterm. Okay, that way we'll have plenty of time to carry on. Now, I did mention yesterday, I believe, that the second midterm is based exclusively on chapters 6 and 7. So probably on Monday, what we'll do is we'll go over the second sample midterm. Okay, we don't have that much time. Remember, the class ends on the 19th. Yeah, we're getting, well, I mean, I don't know. Today's only the 6th, but, it's easy to get complacent and say, oh, don't worry, we've got plenty of time. No, you cannot be complacent in such a short session. So we'll carry on with the new material today and tomorrow. And then on Monday, the 11th, we can go over the sample midterm number 2, which you'll then have the ability to work on. Probably that one can be due on the following Monday. And then the final, of course, we have to review for the final. And since the last day of the class is on the 19th, we'll probably be able, we'll be able to give you a few extra days to take care of the final. And what I will have to do though first is look up the exact date on which they must have the grades. Okay, and then I can let you know when the final is due. But I think we're in pretty good shape. In fact, if anything, we're probably ahead of where we need to be. It's kind of interesting how this is working out. Last spring, when we first started doing everything online, I noticed right away that it's for some reason, I just go through the material more quickly online than in person. So I don't think we have anything to worry about as far as getting all the material done. In fact, we might even be done a little early at the rate we're going. So I guess, well, so that's good. That's good news. The good news is that we're ahead of schedule. So in the meantime, I guess let's just have our break. And then when we get back, we'll start with this brand new chapter and our brand new probability distribution. Okay, I'm sure you're looking forward to that. All right, so I'll see you all in a bit. All right. So let's do this. Let's get back to chapter 9. All right, where are we? All right, so I'll save 8 and then we'll open 9. All right, so now we're going to introduce something new, and you can see for yourselves that it's called confidence intervals. Okay, so in order to do this, we need to introduce some new terminology. So we're going to take a bit of a step back here and review something we've done before, and that is, if you recall from the very first chapter that we covered, that for a population, actually, let's write it like this. 3 of the most important summary measures of a sample or a population are the mean, the variance, and the standard deviation. So when we comes time to calculating this first sample, we use the Roman letters x bar, s squared, and s. For population, we have mu, sigma squared, and sigma. Okay, so nobody has forgotten that. But what we're going to mention here today is that these sample measures are formulas. These on the right are basically considered to be constants because we know what they are. In other words, whatever the population mean is, that is a specific number. So what we would say here then is that x bar is known as a point estimator of mu. And what that means is that x bar is a formula that is used to estimate the value of mu. Okay, so in other words, x bar, the actual x bar you're seeing here is a formula. As of course you recall that it's simply equal to the sum of all the x's in the sample divided by the sample size. So we call that a point estimator. The word point here means that it is a single number. So you're probably wondering, well, what else is there? Well, that's what this chapter is all about. So a point estimator means this is a formula that is designed to give us an estimate of a specific measure, like the population mean. It'll be a single number. So we do the same thing, by the way, with the variance and standard deviation, but we're not going to cover those here. So as opposed to an interval estimator, which we're introducing in this chapter, an interval estimator, on the other hand, is a formula used to calculate a range of values that contains a specific population measure or parameter with a given probability. Now, what does that mean? That's a very complicated sentence. So what I'm going to do is give you an example of this so that it makes more sense. So, all right, let's just say, as an example, suppose that you were to gather up, and let's say you wrote this down. You're somebody who keeps track of everything. Suppose that the number of days, well, all right, let's think about it. No, not the number of days. Let's think about it this way. Suppose that a student records the time that it takes to get to school each day. Okay, fine. So every day you go to school, you write down on a piece of paper how long it took to get to school. And so the mean time that it took, let's say this person's about to graduate. Okay, fine. So you're about to graduate. The mean time that it took for each of these days of traveling could be considered a population. Okay, the population means a list of all the travel times that it took for you to get to school every day while you were in college. Now, the question is, what information do we want to obtain? Suppose that we draw a random sample from those days randomly chosen from these days, and it is determined that the sample mean is 24 minutes. Okay, so the sample mean is a point estimator of the population mean, but 24 is an estimate of the population mean. In other words, we're making a distinction here between the words estimator and estimate. It's a very subtle distinction, but it's important to be aware this is what's happening in the background for all the calculations that we will be doing. You've written down all the times that it took to get to school during your 4 years. That's your population. All those times are the population. You randomly choose a sample from those days, and you find out that during those days, the sample mean was 24 minutes. So the mean itself, the actual X bar formula, is a point estimator of the population mean, which is the average time that it took to get to school for all 4 years. The 24 number that we came up with is defined as an estimate of the population mean. Now, here's the interesting part. This is a very helpful measure to give us a sense of how long it took you to get to school. But while the estimate of 24 is a useful measure of how the average time that it took to get to school, it does not provide any information about how much the commuting time could vary from one day to the next. Okay, so in other words, 24 is the average, but it might be the case that it's almost always within a few minutes. In other words, suppose that, hold on. Suppose, for example, that each day it took at least 22 minutes, but no more than 26 minutes to get to school. Okay, now that's useful information. That means that if you leave the house 26 minutes before your class starts, there's a pretty good chance that you're going to make it on time. On the other hand, as another example, suppose that your path is, or let's say the path you take to get to school is under construction, and the range is actually from 10 minutes to 38 minutes. So in other words, in the first case, it's pretty much the same every day. All right. It can be as little as 22 minutes if you get if you hit all the green lights. If you get all the red lights, it might be as much as 26 minutes. That's a very different experience than the second case, where there's a lot of construction going on. And some days you can just sail along and get there in 10 minutes. And other days it can take as long as 38 minutes. So even if in both cases you have the same average, these are two very different situations. In the second case, if you have an exam that day, you'd better leave the house no more than 38 minutes before the class starts, because otherwise there's a decent chance that you'll be late. Whereas in the first case, you only have to be, let's say, leaving it for 26 minutes before the class starts. So what we're going to do here, in order to incorporate the uncertainty associated with the sample mean, in other words, how much can it change from one sample to the next? So in other words, how much the commuting time can change from one day to the next, we can construct what's called an interval estimate, which includes the sample mean and a range of possible values for the sample mean. So this way you have more information than if you were simply told that the mean is 24 minutes. Okay, so now you can make a distinction between these two cases. The one case where the commuting time is almost identical every day, and in the second case where it can be very different from one day to the next. So that's the purpose of this chapter. We're going to be looking at a specific type of interval estimate, and that is known as a confidence interval. All right, now, what's interesting about these confidence intervals is that we can not only create a range, we can also choose a specific probability for our interval. For example, we can create an interval which has a 95% chance of containing the true population mean commuting time. Okay, so in other words, we also have this notion that we're going to attach a probability to our interval estimate. Okay, so what are we building up to? For example, here, suppose that there's a 95% chance that our population mean is somewhere between 5 and 10. Well, then we can write it out in this form. The probability that mu is somewhere between 5 and 10 is 95%. And this is an example of what we will call an interval estimate. So for example, with your commuting situation, we can say that in the first case, let's say the probability that your time will actually be between 22 and 26. Let me get out the symbol from you, is let's say 95%. In the second case, it's just between 10 and 38. Okay, so you'll see how to adjust these probabilities. Now, our situation is a little bit artificial because we assume that we know the entire population and we can actually just figure out the exact ranges, but most of the time that's not going to be the case. And so that's why this technique is so important. And now the only thing is, though, we have to watch out for, though, is that in order to do this properly, we have to make assumptions. Okay, so let's say, for example, we want to do this with, let's say, the Dow Jones. Suppose we want to know a 95% or an interval estimate. Or how about this, for the price or the rate of return to Apple stock over the coming year. We can do this with historical data, but based on the assumption that the returns to Apple stock are normally distributed. So in other words, that's an important part of this. We don't really have the leisure, or the luxury, I should say, of examining every single return to Apple stock, or at least it would be very time consuming to do that. So what we actually have to do instead is make assumptions about the properties of the returns to this Apple stock. Usually one of those assumptions is that the returns are normal. If we do that, make that assumption, then we can easily construct one of these intervals based on that assumption. So that's what we'll be doing for the most part. All right, so here's how this is going to work. So anyway, the point of all this is that the interval estimate has the advantage that it provides a measure of how much uncertainty there is associated with the true value of the population parameter. The wider is the interval estimate, though, the more uncertain is the parameter. So just like before, in the second case, there's a lot more uncertainty about your commuting time because you don't know from one day to the next if it might take 10 minutes or 38 minutes, where in the first case, you can see that the vast majority of the time, your commuting time will be within this narrow range. So you can pretty much count on getting there on time if you leave the house 26 minutes before your class starts. All right, now, what we're going to do here is now introduce a couple of new terms. An interval estimate in the most general possible terms is constructed as a point estimate plus and minus what we're going to call a margin of error. So if you recall this first case from our commuting example, when we said that the range, so if the range of commuting times is between 22 and 26 minutes, with a mean of 24, then, and I'm running out of space, so I'll move it up here, the point estimate would be 24 plus and minus 2. Okay, in other words, if you notice that the interval is actually 22 up to 26 was constructed as 24 minus 2 and 24 plus 2. So in that case, the point estimate is 24 and the margin of error is 2. Okay, that's how much uncertainty there is associated with our commuting time. For the second case, we had, I'll sneak that in here. Remember, it ranged from 10 to 38. Yeah, big margin of error there. It was 24 then plus and minus 14. Okay, so in other words, that provides us with an interval of 24 minus 14, comma 24 plus 14, which is how we ended up with 10, comma 38. So that's the key detail. The margin of error in the second case is much, much higher because of all the construction. In the first case, there's no construction. So the margin of error is very, very low. It's only 2. So that's the advantage of having an interval estimate compared to a simple point estimate, because again, they both have the same average of 24, but you can see they're two very different situations. And I'm sure you'll all agree that this first one is that you'd rather be in this case or this situation rather than this one, because then you don't know what's going to happen from one day to the next. Whereas here, you're in pretty good shape. You know more or less exactly how long it's going to take. Well, now, how in the world do we actually calculate this with our statistical data? Now, I made up these numbers, of course, but in general, how do you actually calculate one of these intervals? All right, well, there's two approaches that we can take, and they depend. Let me just mention this here. The method we will use to construct what we're going to call a confidence interval for the population mean depends on whether or not the population standard deviation, sigma, is known. If it is, we can use the normal distribution to construct our interval. Okay, so that's good news because we already are very, very familiar with the normal distribution. But what if it isn't? Which, by the way, is the most common case. Most of the time, we do not know the population standard deviation. What happens then? All right, let me copy this slide as we can deal with that right now. Okay, if it is not, we must use a different probability distribution. And I was just going to tell you right up front, known as the t distribution. Okay, and it's also known as the student's t distribution. Now that is something we haven't seen before. That's brand new. When we get to that part of the chapter, we're going to take a stop, a side note basically, and we're going to introduce the t distribution, which it's got a lot of common features with the standard normal, but it's also very different in some important ways. It also has a very interesting history, which we'll talk about, but that is going to be needed to construct confidence intervals when we do not know the population standard deviation, which essentially is the majority at the time. Well, now that one, yeah, luckily that information can be found in our tables or our charts or calculators, but it's a little bit more complicated. We can also use Excel, by the way. And in fact, we'll do that for these cases because Excel has some of this functionality already built into it, just so you can see how that would work. All right, but for now, we'll focus on the calculators and the t-tables, which I did get. There's one here somewhere. I did post it on Moodle, so you can look at it, but you can see it's very, very different than what we're used to. So we'll have to take a few minutes and explain how this table works. And you can see it's very, very different. All right, but like I said, don't panic. All this information is hiding in your calculator. I just have to show you how to use it. All right, so now what really separates, in fact, let me just add that as another detail. The difference between the two cases, in other words, population standard deviation, is known versus unknown. comes down to the calculation of the so-called margin of error. That's really what separates the two cases. How do you calculate the margin of error? Okay. Now, I'm going to show you briefly the formula for calculating the confidence interval when we do know the population standard deviation. Now, do not panic when you see it. Okay, you're going to see tomorrow that it's not a terribly complicated thing to do, but it does require some explanation. Okay, just like every other new concept you've learned in statistics, it looks frightening at first, but when you start to look at it more closely, you'll realize it really isn't frightening at all. Okay, so this is what the formula actually looks like. Well, it doesn't look that bad, but we do need a little bit of an explanation as to what this thing is. And I'll just tell you right up front, this is actually a z-score. But what we still need to discuss is how is this thing calculated? And then we have this new concept here. This is the Greek letter alpha. That is going to need some explanation. So the formula looks fairly straightforward. Now, of course, this is the sample mean. This is the popular. Now, remember, we're assuming that this is known. Otherwise, we can't use the standard normal. Z, of course, remember, is the standard normal distribution. Or think of this as a standard normal random variable. And then, of course, this is our population standard deviation. And here we have the sample size. Okay, so there's at least two things in here that will require some more explanation, but most of it is already very familiar to you. So the right-hand side here, let me mark that off here. Oh, one more thing right here. What is this all about? Plus and minus. I'm sure you've seen this before. It means that what you're actually going to do, let me just mention that on the next slide. Yeah, this formula basically is telling me to do the following. So where it says x bar plus n minus z alpha over 2 sigma radical n, this piece on the right-hand side is the so-called margin of error. But this formula basically tells me to create an interval in the following way. We're going to have a lower limit of x bar minus the margin of error. And then we're going to have an upper limit consisting of x bar plus z alpha over 2 sigma radical n. Okay, so in other words, the formula that you're seeing on the top is a shorthand way of expressing what we see in the bottom. We have a lower limit to this interval, we have an upper limit. And the difference between the two is whether we add or subtract the margin of error. Okay, so remember this is my margin of error. So basically our strategy is to calculate the margin of error and then essentially just add and subtract it from x bar, and that will give us our confidence interval. And then we're done. Well, of course, as usual, it's not quite as easy as it sounds, but that in a nutshell is what we're doing. Okay, that's where we're going with this. Now, tomorrow, of course, is Thursday, our last meeting of the week. And after this, you'll need a weekend to recover, I think, especially since several things are due the following Monday. But I don't know. I think you have plenty of time to take care of this. But yes, we do need to get into this more deeply. And then also, oh man, boy, this is really getting to be a bit much, but I think our best strategy as far as reviewing goes is to work on the sample midterm number 2, not tomorrow, but next Monday. So yeah, I can see the work is piling up a little bit, but I mean, this is an intense session, but I still think you have plenty of time to do it because the sample midterm is just 6 and 7. Okay. 6 is our discussion about the discrete random variables. 7 is our discussion about the continuous ones. And in fact, if we go to Moodle, which I believe is still open here, and open this up for a second, you'll see that everything in the second sample midterm should be very familiar to you. Where is it? Okay, there it is, there it is. So if you look at these problems, these are all, short answers based on chapter 6 and 7. And then we have discrete probability distributions, and we have continuous probability distributions. Okay, so no, I think you'll be in pretty good shape here. So tomorrow we'll carry on with chapter 9. We'll introduce or get more deeply into this discussion. And then next Monday, we can go over the sample midterm. It might take the whole period, it might not, I don't know. But that's okay, we've got plenty of time. We're actually, like I said, ahead of schedule. So we got plenty of time to review, and then we'll take it from there. All right. So yeah, I know it's a little early, but I think we better stop here because what's coming up next is going to be a little bit more involved. So what I'd like to do tomorrow is take a step back and review everything we've done here in chapter 9, just to make sure we all are on the same page. And then we'll get cracking on our calculations. And then, as our big bonus surprise for tomorrow, we'll introduce the t distribution, which is, you'll discover pretty quickly, if there's one distribution that's used almost as much as the normal, it would be the t. So it turns out to be extremely important. All right. So I guess, unless there's any questions, I will see you all tomorrow.
I do have a quick question.
Okay.
Any idea of when we'll get some of our corrections back?
Oh yeah, I'm working on that. I'll probably have them done. Today's Wednesday, isn't it? I'm aiming for tomorrow, if not tomorrow morning, tomorrow afternoon or evening. What I have to do is I will actually be posting the solutions. And then, see, now this is very awkward compared to being in person where I can just physically hand it back to you. What I will do is I'll post the solutions, I'll post the grades. Actually, no, yeah, I think there's a way I can put the grades in Moodle. I'll have to investigate that. And what I'll do is I'll post the solution so you can see what the right answers were. And then what I can do is, if people want that, I can send you an email which I tell you which questions you got wrong. I'm not sure what else I can really do. And then if you want to go over in more detail, you can either send me an email or we can get together on Zoom separately. Okay, so it won't take too much longer.
Awesome. How about the midterm around the same time frame? Or
the midterm is due on Monday. So, yeah, I mean, if you need to know, like, if your anxiety levels are going through the roof and you need to know right away, I mean, I can put yours at the front of the list.
I was just curious.
Okay, no. It's just, if you really have to know, just send me an email and say, listen, I'm dying. I need to know now what my midterm score was. And so what I'll do is I'll do yours first.
Okay. Sir, thank you very much. Sorry.
Okay, all right. Anyone else? Oh, we got a question. Have a good day, you too. Anyone else? All right, so see you all tomorrow.